Hello everyone, my name is Yörükoğlu and today I will present my term project, which is a TurtleBot3 based autonomous warehouse navigation system. As industrial logistics continues to grow, companies need more efficient, safer and automated solutions for transporting goods inside warehouses. To address this need, I developed a complete autonomous navigation workflow using Roast2 Humble and the TurtleBot3 Burger robot. The main objective of this project was to combine mapping, localization, and autonomous navigation into a single system that can operate in a simulated warehouse environment. The project was divided into 4 main stages. First, I designed a warehouse environment in Gazebo. Then, I generated a map using a SLAM algorithm. After that, I performed robot localization using AMCL. Finally, I implemented autonomous navigation with the Nav2 framework. Together, these stages create a complete workflow that allows the robot to understand its environment and move autonomously toward a target location. For the simulation environment, I used Gazebo and the TurtleBot3 Burger robot equipped with a simulated 2D LiDAR sensor. The warehouse layout was designed in an H shape to create realistic navigation challenges. It includes narrow corridors, structural pillars, and storage boxes that can act as obstacles. This environment allowed me to test the robot's ability to detect obstacles and navigate safely throughout constrained spaces. In the mapping stage, I used Google Cartographer SLAM. The robot was manually driven throughout the warehouse using the TurtleBot3 teleoperation package. While moving, the LiDAR continues to scan the surroundings and generated a map of the environment. After the mapping process was completed, the occupancy grid map was saved as YAML and PGM files using the Nav2 map server. This map was later used for localization and navigation. Once the map was created, the next step was localization and navigation. For localization, I used adaptive Monte Carlo localization, which is AMCL. This method uses a particle filter to estimate the robot's position by comparing live LiDAR scans with the saved map. For navigation, I used the Nav2 framework. The global planner calculates the best path to the destination, while the local planner adjusts the robot's movements to avoid obstacles. A behavior tree coordinates these components and handles recovery actions if the robot encounters difficulties. The project successfully achieved full integration of all navigation stages from environment initialization and mapping to localization, path planning, and autonomous goal reaching. One of the main challenges was localization drift and map inconsistencies. These issues were reduced by adjusting cost map parameters and improving the mapping process. In conclusion, the system demonstrated a reliable navigation and obstacle avoidance capabilities. Future work could include multi-robot coordination, dynamic obstacle tracking, and deployment on a real TurtleBot3 platform. Thank you for listening, and now I'm gonna show you a video of my project working. So this is my RV screen, which is in a map. And this is Gazebo, my 3D world. And those are my 4 terminals, including RVs, Gazebo, teleoperation, and navigation. So in RVs, I choose Nav2 to choose a spot I want my robot to go. And as you can see, the robot calculates the best way to go to that spot and goes to the spot where I want it to go. I sped up this part because it was a little long. And after that, I can choose another spot and the robot will calculate the best way and go there without bumping to any obstacles and finding its best route. So this is another navigation or the best way for my robot, which it found. So this was my MC330 course term project presentation. Thank you for listening.